Okay, pre-calc. Here is our recording for graphing cosecant and finding its inverse. So let's start with a parent function, which is a table. So let me move over here. Now with cosecant, what you want to do is you might want to start with sine value. Oh, that's a bell at the end of fifth period. Okay, so you want to start out with the sine value and then maybe just do the reciprocal because that's exactly the same thing. Okay, so here we go. Sine of 0 is 0, but in cosecant world, it's going to be undefined. So sine of pi over 2 is 1. With cosecant, it's also 1. Sine of pi is going to be 0. Sine of pi is 0, so the reciprocal is going to be undefined. 3 pi over 2, sine 3 pi over 2 is going to be negative 1, so cosecant is also negative 1. Sine of 2 pi is back at 0, so that means cosecant is going to be 0. So what is happening is I'm going to do a period to the left and a period to the right. And I'm going to have a few asymptotes, as you can see, starting at 0. Okay, and then there's another asymptote at pi and 2 pi, and similarly to the negative period. Okay, so if you remember, cosecant and secant are going to have u's. So these are going to be parabolas opening up in that way, and down here parabolas opening down, and that means this is now repeating. So this is going to be opening down, and this is going to be opening up. Okay. So that's the regular function for graphing cosecant. Now, as you can see, cosecant is not a one-to-one, okay? Because the answer is no. We have to restrict its domain so you can be a one-to-one function. Now, the whole purpose of restricting its domain, so that way when you find its inverse, the inverse is also a one-to-one. Next, we have to decide on where you're going to cut this off. So I'm going to highlight a couple of things. It may not be true at first, okay? So just kind of listen. So what if I were to restrict it from 0 to pi? Well, that's not a one-to-one. That's not going to work, right? So unhighlight that. What if I want to say 0 all the way to 2 pi? Well, that's definitely not a one-to-one. So unhighlight that. What if I want to go negative pi to 0? Well, that's not a one-to-one because this piece is not a one-to-one, right? So definitely unhighlight that. Okay. Then what you want to do is from here to here. Oops, why did I erase that? So what we're going to highlight is this right here. A little bit of that and a little bit of this, right? So what we are really taking is this piece, okay? And what we're really taking is this piece right here. That piece. So those are the pieces that we are going to take, okay? Including this and including this. So as you can see, there's an asymptote in the middle, okay, which we have to take into account. So restrict its domain, we can write this multiple ways. We can say, well, inclusive from pi over 2 to pi over 2, but definitely never ever be 0, right? Or we can write it in interval notation because that's a little bit better. It's going to be from negative pi over 2, take a break at 0, union that with 0 to pi over 2 inclusive at the end. I like this way better because it looks like it's more connected. Okay, so now let's go and find the inverse. The inverse by definition is really just switching y and x. So x equals cosecant of y, which, because we have to solve for y, that's why we're now going to compose both sides by cosecant inverse, which by definition, cosecant inverse, the inverse notation is really using this symbol right here. So that's my cosecant inverse. Let's state the domain for cosecant inverse and the range of cosecant inverse, okay? The domain of cosecant inverse is where you want to go and look at the range, okay? So the range of cosecant is from negative infinity, take a break at 1, right, of negative 1, and then from 1 all the way to infinity. So that's your domain. So negative infinity all the way to 1, negative 1, I'm sorry, take a break, union that with 1 to infinity. That domain of the cosecant inverse comes from the range the range of your regular cosecant. Now, the range of cosecant inverse is where you have to look at our restriction, where we cut it off. So that's going to be negative pi over 2 all the way to 0. Union that with 0 to positive pi over 2 and inclusive. Don't forget the comma right there, okay? Yes, it's just like sine and cosine and tangent. The domain and range, super important, right? When we're trying to find the exact value. So now let's put these together on the same coordinate plane to see what it looks like. So first I'm going to graph normal function first, restricted, okay? I'm just going to go as far as pi over 2. Pi over 2, negative pi over 2, up pi over 2, and negative pi over 2. That means 1 is 2/3 of the way. So this is about 1, okay? 1, 1, negative 1, negative 1. That means pi over 4 is max center. I don't need pi over 4 that much, but might as well write it. Okay, so this is pi over 4. Pi over 4. Okay, so here we go. I will start out with an asymptote for my regular function. Okay, so here's an asymptote. And all I'm doing is really copying this right here. You see that? So, as you can see, at pi over 2, cosecant is going to be 1. So make a dot at 1 right there. And I'm going to head towards the asymptote. So close dot. And at negative pi over 2, I'm going to make a dot at negative 1. And again, head towards my asymptote. So this green piece right here is y equals cosecant of x, normal with restricted domain. Now I'm going to use red to do the inverse. Let me label the points for you. This is pi over 2, comma 1. This is negative pi over 2, comma negative 1. Okay. So the inverse, if you had a vertical asymptote before, now it becomes a horizontal asymptote. Okay. Now again, I'm doing red. F inverse of x equals cosecant inverse of x is the red piece. This point used to be pi over 2, comma 1, so now it's going to be 1, comma pi over 2, which is that piece. And remember, you're going to be heading towards your asymptote, so go that way with an arrow. Then the other piece, it used to be negative pi over 2, comma negative 1, so now I'm going to go negative 1 and negative pi over 2, and again, head towards your asymptote. So as you can see, hopefully, if I were to graph this out perfectly, it should be symmetrical about this line, right? And this line is called y equals to 2x. Okay, so kind of pinching this in, okay? What I did was, this is the normal, right? This red piece, and that's where we get that's on the bottom, and then the red is your cosecant inverse. Okay, and again, always check to see if it's symmetrical about the line y equals x. And this is, I believe, the end of cosecant inverse.